Hello, good evening, Achyut.
Good evening, sir. Can you hear me?
Yes, I'll share the file.
Sure, sir. We can continue.
So we had discussed till here.
Yeah.
So next, chemical properties of carboxylic acids. So carboxylic acids, they are acidic in nature, so they can react with metal to form salt and liberate hydrogen gas. So it reacts with sodium to form sodium carboxylate. Hydrogen gas is released. Then being acids, they can react with base to form salt and water. So carboxylic acid reacts with sodium hydroxide to form sodium carboxylate and water.
Yeah.
Then carboxylic acids, they are stronger acids than phenols. And phenol is stronger than water. Water is a stronger acid than alcohol. So carboxylic acid, they are stronger than both phenols, water and alcohols. So
Yeah.
these two reactions, the reaction with metal and with sodium hydroxide, these two reactions, they are also shown by alcohols and phenols. Okay? And so we can distinguish phenols from carboxylic acids by using this reaction. Like we can react the carboxylic acid with carbonate or hydrogen carbonate, metal carbonate or metal hydrogen carbonate. Carbon dioxide gas will evolve. So there'll be a brisk effervescence of carbon dioxide. So this reaction is shown only by carboxylic acid and not by phenols. So this reaction can be used to distinguish between carboxylic acid and phenol. Phenol will not undergo this reaction. Now, the carboxylate anion is resonance stabilized, which accounts for the acidic nature of the COOH group.
Yeah.
So carboxylic acid, when I dissolve it in water, it will give up its H plus ion. Water will become hydronium ion. And when carboxylic acid gives up its H plus ion, it will become carboxylate anion. This carboxylate anion is resonance stabilized. The negative charge is shared between both the oxygen atoms. And so it is resonance stabilized. And since it is resonance stabilized, it can form easily. And since it can form easily, carboxylic acid must be an acid. That accounts for the acidic nature of the COOH group.
Yes.
So anyway, they are weak acids, means they undergo this ionization only partially. They dissociate only partially when dissolved in water. So they are weak acids, and equilibrium will be established between undissociated molecules and the ions. The equilibrium constant is given by this expression. So this is nothing but, in the numerator, you are having product of molar concentrations of the products. In the denominator, you are having product of molar concentrations of the reactants. So these concentrations are the equilibrium molar concentrations. Okay. So generally we take water as a solvent. So generally water will be taken in large excess. So change in concentration of water is negligible, or concentration of water is almost a constant. So we can define a new constant. So concentration of water is constant. So I can bring this water to the left side. So KEQ into water. So that gives a new constant, which is called as acid dissociation constant. So acid dissociation constant is equal to H3O plus into RCOO minus divided by RCOOH. Okay. So this is the acid dissociation constant. higher the value of Ka, greater will be the this one acid strength. So stronger will be the acid. Higher the Ka value, stronger will be the acid. Then we have pKa. pKa is equal to minus of log Ka. So smaller the pKa value, stronger will be the acid. Smaller the pKa, stronger will be the acid. Okay, so acid. So here we have some examples which illustrate the acid strength. So for a mineral acid like HCl, it is pKa is -7. And among organic acids, CF3COOH, trifluoroacetic acid, that is the strongest acid among all the organic acids, and it has pKa value is 0.23. For benzoic acid, 4.19. For acetic acid, 4.76. So we can see over here that benzoic acid has lower pKa value than acetic acid. So benzoic acid is a stronger acid than acetic acid.
Yes, sir.
Okay. So carboxylic acid, stronger acids than phenols. Phenol is stronger acid than water. Water is a stronger acid than alcohol. So carboxylic acid. So now comparing carboxylic acid and simple phenols. In phenol, suppose on the benzene ring, in phenol on the benzene ring, if there are too many electron withdrawing group, then that becomes as acidic as a carboxylic acid. So here we'll consider only simple phenols. So carboxylic acids, now why carboxylic acids are more acidic than phenols? So let us look at the resonance structure. If carboxylic acid loses a H plus ion, it will become carboxylate ion. This carboxylate ion is resonance stabilized. If phenol loses H plus ion, it will become phenoxide ion. Phenoxide ion is also resonance stabilized. In fact, phenoxide ion is having more number of resonance structures. But still, carboxylate ion only is more stable because in carboxylate ion, the negative charge is shared between the oxygen atoms. So oxygen is more electronegative than carbon. In carboxylate ion, the negative charge is shared between the more electronegative oxygen atoms. Whereas in phenoxide ion, negative charge is shared by oxygen atom only in one resonance structure. In other resonance structure, it is shared by the less electronegative carbon atom. So because of this, phenoxide is less stable than carboxylate, or carboxylate is more stable. Since carboxylate anion is more stable, it can form more easily. So carboxylic acid is a stronger acid than phenol.
Yeah.
Okay, so this is the equation. So when carboxylic acid is dissolved in water, it will give H plus to water. We get hydronium ion, and carboxylic acid gets converted to carboxylate anion. So more easily this carboxylate anion is formed, stronger will be the acid. So obviously now carboxylate anion will be more stable. More stable it is, more easily it will form. So carboxylate anion will be more stable if we are having electron withdrawing group in the R. In R, if I'm having electron withdrawing group, it will be more stable and the acid will be a stronger acid. If I'm having electron donating group, okay, so that will increase the electron density on the carbon. So it will destabilize. Having electron donating group will destabilize. So it will be a weaker acid.
Yes.
So RCOOH is stronger acid if it contains electron withdrawing group. So for example, ClCH2COOH is a stronger acid than CH3COOH. RCOOH is a weaker acid when R contains an electron donating group. So CH3, for example, CH3COOH is a weaker acid than HCOOH. So HCOOH is the simplest carboxylic acid. And the next homologue is CH3COOH, which is having one alkyl group extra. So alkyl group is electron donating group. So CH3COOH is a weaker acid.
Yes.
Okay. So next, higher the electronegativity of the substituent, greater, stronger will be the acid. So CF3COOH is a stronger acid than CCl3COH because fluorine is more electronegative than chlorine. Among carboxylic acids containing same kind of substituent, carboxylic acid with higher number of electronegative substituent is a stronger acid. So CCl3COOH is stronger acid than ClCH2COH. So CCl3 is having 3 chlorine groups, whereas this is having only 1. So greater the number of electronegative substituent, stronger is the acid. Then closer the electronegative group to the COOH group, stronger will be the acid. So ClCH2COOH is a stronger acid than ClCH2CH2COH. So in ClCH2COH, Cl is present on the second carbon, whereas here in ClCH2CH2COH, Cl is present on the third carbon. So closer the chlorine or the electronegative group to the COH, stronger will be the acid. So ClCH2COH is the stronger acid. The effect of some groups on increasing the acidity of carboxylic acid is in the following order. So CF3 is having the highest effect. Okay. So it is having higher effect than nitro. Nitro higher effect than cyano, higher effect than fluoro, chloro, bromo, iodo, and that has a higher effect than the benzene ring. So even benzene ring has the ability to increase the acidity. So the following is an arrangement of carboxylic acids in the order of their acidity. So CF3COH stronger acid than CCl3COH because fluorine more electronegative than chlorine. This is stronger acid than CHCl2COH because this is having 3 chlorine, this is having only 2 chlorine. This is stronger acid than NO2CH2COH because NO2 is having a greater effect. And this is stronger acid than CnCH2COH, which is stronger than FCH2COH, stronger than ClCH2COH, that's stronger than BrCH2COH, and this is stronger than HCOOH, and this is stronger than ClCH2CH2COH. This is stronger than the benzoic acid, benzene ring COH, which is stronger than benzene ring CH2COH, and that is stronger than CH3COOH, which is stronger than the CH3CH2COOH.
Yes.
Okay, next let us compare between acrylic acid and propionic acid. So propionic acid or propanoic acid. Propionic acid is common name. Propanoic acid is the IUPAC name. So propanoic acid is CH3CH2COOH. Okay. So here the respective carboxylate is shown over here. Carboxylate of propanoic acid is shown over here.
Yeah.
Here, carboxylate of acrylic acid or prop-2-enoic acid is shown over here. So in prop-2-enoic acid, the COOH group will be attached to sp2 carbon. Whereas in propanoic acid, the COOH group is attached to a sp3 carbon. We know sp2 carbon is a more electronegative than sp3 carbon. sp2 is more electronegative than sp3. So prop-2-enoic acid will be a stronger acid than propanoic acid.
Yeah.
And then one more reason, if you look at the resonance structures of the carboxylate anions. So carboxylate of acrylic acid or prop-2-enoic acid, it is having 3 resonance structures. Whereas propanoic acid, carboxylate of propanoic acid, it is having only 2 resonance structures. So higher the number of resonance structures, greater will be the stability. So carboxylate of prop-2-enoic acid is more stable than carboxylate of propanoic acid. So prop-2-enoic acid will be a stronger acid than propanoic acid. So 2 reasons. One is prop-2-enoic acid, COOH is attached to sp2 carbon. Here COOH is attached to sp3 carbon. And then this is the carboxylate is having 3 resonance structures. In the propanoic acid case, the propanoic acid carboxylate, it has only 2 resonance structures. For these 2 reasons, prop-2-enoic acid is a stronger acid than propionic acid or propanoic acid.
Yeah.
Okay. Then, so when it comes to benzoic acids, so if we are having electron withdrawing group, that will increase the acidity. If there is electron donating group, it will decrease the acidity. Now, in case of benzoic acid, electron withdrawing, electron donating, they can happen by means of inductive effect. They can also happen by means of resonance effect. Now, in case of methoxy group is having oxygen. Oxygen is highly electronegative in nature. But what happens? Lone pair of electron on oxygen, it participates in benzene ring. Therefore, electron density on the carboxylic acid group increases. So the acidity decreases. So methoxy group increases the electron density by means of plus resonance effect or plus mesomeric effect. Methoxy group increases the acidity. Methoxy group increases the electron density by means of plus resonance effect or plus mesomeric effect. It increases the electron density and therefore decreases the acidity. Nitro group, it decreases the electron density on COOH group by means of minus resonance effect or minus mesomeric effect, and therefore it is a stronger acid. It increases the acidity. So among these three, 4-nitrobenzoic acid is the strongest acid. It is stronger than only benzoic acid, and only benzoic acid is stronger than 4-methoxybenzoic acid. So if you look at the pKa value, 4-nitrobenzoic acid is the strongest acid among these three, and it has the highest pKa.
Yes, sir.
Next, formation of anhydride. So carboxylic acids, they undergo condensation reaction with elimination of small molecules such as water itself in case of this carboxylic acid. And so they form what is called as acid anhydride. The reaction is catalyzed in presence of an acid such as concentrated sulfuric acid or phosphorus pentoxide. So two molecules will combine. Hydrogen from one molecule, OH from the other molecule. They go out as water. So it's a condensation reaction, and the product that is formed is called as an anhydride. It is a carboxylic acid anhydride or simply acid anhydride. So the reaction is done by heating the carboxylic acid in presence of concentrated sulfuric acid or P2. Concentrated sulfuric acid or P2O5, they are called as dehydrating agents. Next, esterification. So carboxylic acids, they react with alcohols in presence of small amount of concentrated sulfuric acid or HCl gas. We should not use HCl solution. We should not use, because if we use solution, there will be lot of water, and that will promote the reverse reaction. So we can use HCl gas, but not HCl solution. Even sulfuric acid also concentrated sulfuric acid, not dilute. So hydrogen of the alcohol, OH of the carboxylic acid, they go out as water. And hydrogen of the alcohol gets replaced by RC double bond O. So R double dash O, RC double bond O. So RC double bond O, OR dash. So this is nothing but esters. And when this ester, it is having a fruity odor. So when I do this reaction in a beaker or in a test tube or beaker, so from the reaction mixture, I'll get, when the product is formed, when ester is formed, I'll get a fruity odor. So when I get fruity odor, I can understand that the given compound is a carboxylic acid. So this reaction serves as a test for carboxylic acid. So esterification mechanism, I guess you won't be having this mechanism.
This mechanism we don't only know the reaction.
Then reaction with chlorinating reagents for phosphorus trichloride, phosphorus pentachloride, thionyl chloride. So in whatever way these reagents react with alcohol, in the same way they react with carboxylic acids. So in alcohol, they replace OH with chlorine. In carboxylic acid also, they replace the OH of carboxylic acid with chlorine. So we get acid chloride or acyl chloride. So RCOOH plus PCl5. will give RCOCl plus POCl3 plus HCl. RCOOH plus PCl3 gives RCOCl plus H3PO3, phosphorus acid. RCOOH plus thionyl chloride, SOCl2, gives acid chloride plus sulfur dioxide plus HCl. So just like in the case of alcohols, over here also, if I want to prepare an acid chloride, using thionyl chloride is the best method, because when I use thionyl chloride, the byproducts are sulfur dioxide and HCl, which are gases. They just escape. It becomes very easy to isolate and purify the acid chloride.
Yes.
Then reaction with ammonia. Okay. So carboxylic acid will react with ammonia to form ammonium carboxylate salt. So carboxylic acid, it's an acid. Ammonia is a base. So first thing is acid-base reaction will happen. We get a salt, ammonium carboxylate salt. This on heating to high temperature will give an amide. So CH3 C double bond O NH2. That is amide. So this particular example is called as acetamide. So benzoic acid with ammonia will give ammonium benzoate. This on heating will lose water molecule. So here also there is loss of water molecule and there is formation of benzamide.
Yes.
Okay. So this is phthalic acid. It's a dicarboxylic acid. Common name is phthalic acid. So this, if I react with two equivalents of ammonia, so I'll get ammonium phthalate. This on heating to high temperature. So it will get converted to the amide, CONH2, CONH2. Two amide functional groups are there. And this on strong heating, there'll be condensation between these two groups. Between these two groups, there'll be condensation with elimination of ammonia molecule. So I get the formation of this product, which is called as phthalimide. Next, reduction of carboxylic acid to primary alcohol. So it can be reduced using lithium aluminum hydride or diborane. So diborane is a better reducing agent than lithium aluminum hydride, because lithium aluminum hydride is a very strong reducing agent. If any other functional group is there in the molecule other than COOH, lithium aluminum hydride will reduce the other functional group also. Whereas borane, it will not readily reduce other functional groups. It will reduce mainly COOH only. It does not easily reduce other functional groups such as ester, nitro, halo. So diborane is a better choice. Sodium borohydride, it cannot reduce carboxylic acid. Sodium borohydride is a mild reducing agent. It cannot reduce carboxylic acid. It can only reduce aldehyde and ketone. So I can react carboxylic acid with lithium aluminum hydride in ether as solvent, or I can react carboxylic acid with diborane, followed by treating the product mixture with aqueous solution of an acid. I'll get the primary alcohol. So reduction of carboxylic acid will give only primary alcohol. Okay, Chit?
Yes.
Okay. So we are familiar with this, that is carboxylic acid, sodium salt of carboxylic acid upon decarboxylation will give an alkane. This is a method of preparation of alkene. So when sodium carboxylate is heated with soda lime, soda lime is a mixture, 1:1 mixture of sodium hydroxide and calcium oxide. Carbon dioxide is lost, and thereby the carboxyl functional group is removed. Okay. So carbon dioxide goes out. So that means it will no more have the carboxyl function group. So it's a decarboxylation reaction. And then a hydrocarbon is formed. So RCOOH with sodium hydroxide will give RCO minus Na plus. And that on heating with sodium hydroxide and calcium oxide, I'll get RH and sodium carbonate.
Yeah.
Then we can also do decarboxylation by Kolbe electrolysis. So by electrolysis of aqueous solution of alkali metal salt of carboxylic acid. Aqueous solution of alkali metal salt of carboxylic acid. upon electrolysis. So from RCOO minus Na plus, I'll get RR. So the product is a hydrocarbon containing twice the number of carbon atoms present in the alkyl group of the carboxylic acid. So it is Kolbe electrolysis. Then we have halogenation. So halogenation by Hell-Volhard-Zelinsky reaction. So this reaction is shown only by those carboxylic acids which are having alpha hydrogen, at least one alpha hydrogen. So the carbon which contains COOH group, that carbon is the alpha carbon. Hydrogen attached to alpha carbon is the alpha hydrogen. So only those carboxylic acid which have at least one alpha hydrogen undergo this reaction. So carboxylic acid containing alpha hydrogen is treated with a halogen such as Br2, generally Br2 or even Cl2 in presence of red phosphorus. And then the product mixture is treated with water after the reaction. After the first step, the reaction mixture or the product mixture is treated with water. We get alpha halocarboxylic acid.
Yeah.
Okay. So then aromatic electrophilic substitution reaction. So COH group, it is an electron withdrawing group. So it decreases the electron density in the benzene ring. It decreases the reactivity of the benzene ring towards electrophilic substitution reaction. And therefore, it is a deactivating group. Okay. And then it decreases the electron density, particularly at ortho and para position. Electron density is decreased, particularly at ortho and para position. So electron density at meta position will be relatively higher than electron density at ortho and para position. Therefore, when this is subjected to electrophilic substitution reaction, the substitution will happen at meta position. So we get, so suppose if I do so, COH is a meta directing group. COH is deactivating group and meta directing group. So if I do nitration of benzoic acid, I'll get meta-nitrobenzoic acid. Or if I react benzoic acid with bromine in presence of FeBr3 as catalyst, so halogenation will happen. I'll get meta-bromobenzoic acid. Okay, Achyut?
Yeah.
Okay, Achyut, that's it about this chapter.
Yeah, sir. Sir, could you show the equations part from this chapter?
Equations.
Yeah, yes, sir. Could we go through that part once?
From the beginning,
Yeah, sir. Only the equations part.
okay. So here these oxidation reactions. So like you take a primary alcohol, you treat with chromium trioxide, you get an aldehyde. Here you don't require, like these are, the reactions will be quite complex. You don't need a balanced chemical equation in case of these reactions. Or if you want, you can use nascent oxygen. So using nascent oxygen, you can show, like you can write a equation, but generally they don't write a balanced chemical equation for these reactions. Then dehydrogenation of alcohols. So vapors of the alcohol is passed over metal catalyst to form aldehyde or ketone. So hydrogen gets removed over here. So here you can write say for primary alcohol, you can write RCH2OH is passed over heated metal catalyst such as silver or copper at about 573 Kelvin. So we get the formation of RCHO and hydrogen. So similarly, secondary alcohol will get CH, OH, R dash. So this on passing vapors of secondary alcohol or heated copper at 573 Kelvin. So we get the formation of ketone R C double bond O R dash plus hydrogen. Then ozonolysis. So you treat an alkene. Say, let us take some model example. Say CH3, C double bond C. And suppose this is also CH3. And this side we can keep, okay, one CH3 and one hydrogen. So this on reacting with ozone. So it will give the ozonide. Ozonide is this one. And then it will have the substituents. CH3, 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 hydrogen. And this on treating with zinc dust, finely powdered zinc, and then water. So first zinc dust and then water. So we get the formation of the this thing. So I'll get ketone. So I'll get CH3, C double bond O, CH3. And then the right side, that will give aldehyde. C double bond O, CH3, H. CH3, CHO. Okay, Achit?
Yes, sir.
So hydration of alkynes. So it is nothing but acid catalyzed addition of water. So the catalyst is sulfuric acid and mercury sulfate. So we can write the complete formula H2SO4, HgSO4, or sometimes it is also written as H plus Hg2 plus. In this way also it is written. But if you want to show the reagent completely, you can write H2SO4, HgSO4. So it is addition of water across carbon-carbon triple bond. So we can just write the product. Okay, Achit?
Yeah.
Then Rosenmund reduction. So acid hydrogenation of acid chloride or acyl chloride over palladium supported on barium sulfate. So hydrogen will react with this. It is a hydrogenolysis. So this bond will break. One hydrogen atom will form bond with the carbonyl carbon, one hydrogen atom with chlorine. So you'll get this plus HCl. Plus HCl you will get. Or if you want to write a general equation, it will be R C double bond O Cl, giving R C double bond O H plus HCl. Next, we have Stephan reaction. So RC triple bond N is reacted with stannous chloride in presence of HCl. So we get the formation of RCH double bond NH. Okay. So yes, stannous chloride is a catalyst. You can write it above arrow mark. It doesn't come in the balanced chemical equation. You can like if you don't want like if you are looking for a balanced chemical equation, then you can avoid this. You can just write it above arrow mark.
Yeah.
So the reaction is, the mechanism is quite complex. You can write both SnCl2 and HCl above arrow mark, and we get RCH double bond NH. So net effect is as if hydrogen has been added across carbon-nitrogen triple bond. But here there is no hydrogen molecule is not created over here. But the reaction mechanism is such that the net effect is addition of hydrogen across carbon-nitrogen triple bond. So we get RCH double bond NH, which is called as an imine. This on acid hydrolysis will give aldehyde and ammonia. So under acidic condition, that ammonia will become a salt. So we'll get that ammonium salt. So we get aldehyde and ammonium salt. Okay, Akshat?
Yes.
Then reduction of nitrile or ester using diisobutyl aluminum hydride, ALH diisobutyl. So it is diisobutyl aluminum hydride. So it is abbreviated as DIBAL. So they are given the example of this. Why they are given this example? To show that diisobutyl aluminum, it will not reduce all functional groups. It is selective. It is milder than lithium aluminum hydride. So here it is reducing only carbon-nitrogen triple bond. It is not affecting carbon-carbon double bond. So that's what they want to demonstrate over here. So diisobutyl aluminum hydride on the arrow mark. So we get this one. So carbon-nitrogen triple bond is reduced to carbon-nitrogen double bond, CH double bond NH.
Yes.
This on treating with aqueous solution of an acid. So this hydrolysis happens over here. So we get the formation of this aldehyde and ammonia is liberated. But since conditions are acidic, we get ammonium salt. Then ester. So this is example of an ester. So if I use lithium aluminum hydride, if I react ester with lithium aluminum hydride, I will get a primary alcohol. Okay. So lithium aluminum hydride will reduce the ester to aldehyde, and that aldehyde in the same reaction mixture, it will undergo over reduction into alcohol. But in case of DIBAL, it is possible to control the reduction to aldehyde stage. Over reduction to alcohol will not happen. So treat the ester with diisobutyl aluminum hydride, and followed by, after the reaction is over, treat the reaction mixture with aqueous solution of an acid. We get the respective aldehyde. So the aldehyde is formed. And maybe this part that will form the alcohol, CH3, CH2, OH.
Yes.
Then we have, so for making benzaldehyde, so we have ETAD reaction. So toluene methyl benzene is treated with CrO2Cl2 in carbon disulfide as solvent. So we get this chromium complex, benzene ring CH, OCrO, HCl2 twice. This on treating with aqueous solution of an acid, we get the benzaldehyde. Then oxidation of toluene using chromium trioxide and acetic anhydride. So toluene will react with chromium trioxide and acetic anhydride. Both are required at low temperature. So 273 to 283 Kelvin, 0 to 10 degrees Celsius.
Sir,
So we
suppose they
get,
write only 273 or 283, will it be fine?
okay, if you want to write, then write 273 instead of 283.
Okay, yes. No, I mean, like, in case I forget that range, just
Yeah,
remember
okay, if you forget, no problem, you can forget this one, but this one you have to remember.
Okay, yeah.
Because, see, if it is lower, no problem, it should not become higher.
Yeah.
So we get benzylidene diacetate. And this on treating with aqueous solution of an acid, heating with aqueous solution of an acid, we get the formation of benzaldehyde. Then commercial method. So toluene is reacted with chlorine in presence of light of suitable wavelength. So we get the formation of benzyl chloride. And this on heating with water to 373 Kelvin. So we get benzaldehyde. Then Gutterman-Koch reaction. So benzene is reacted with carbon monoxide and HCl, and both are required, carbon monoxide and HCl, in presence of anhydrous aluminum chloride and cuprous chloride or copper 1 chloride. So we get benzaldehyde.
Yes.
Then preparation of ketones using dialkyl cadmium and acyl chloride or acid chloride. So dialkyl cadmium, acid chloride. Dialkyl cadmium, the alkyl group will be nucleophilic in nature. So two alkyl groups are there. One of the alkyl group will attack this carbon. Chloride will go out. We get a ketone. And other alkyl group will attack carbonyl carbon of another molecule. So two molecules of ketone are formed. And that chlorine will combine with cadmium to form cadmium chloride. So two equivalents of acyl chloride or acid chloride with one equivalent of dialkyl cadmium will give two equivalents of ketone and one equivalent of cadmium chloride. So next, so how to prepare this dialkyl cadmium? So we can react Grignard reagent with cadmium chloride. So Grignard reagent can be alkyl magnesium halide or it can also be phenyl magnesium halide. Anything will do. R can be alkyl group or aryl group. So that is reacted with cadmium chloride. We get dialkyl cadmium and the magnesium salt. So two equivalents of Grignard reagent with one equivalent of cadmium chloride will give one equivalent of dialkyl cadmium and two equivalents of the magnesium salt.
Yes.
So addition of Grignard reagent to nitrile followed by hydrolysis. So we are going to add Grignard reagent across carbon-nitrogen triple bond. So R1 will form bond with carbon, magnesium will form bond with nitrogen, MgBr will form bond with nitrogen. So the reaction is done in ether as solvent, anhydrous ether as solvent. So we get R, C double bond N, MgBr, then R dash, C, RC, R dash. So with C double bond N, MgBr. So this on treating with aqueous solution of an acid. So here hydrolysis takes place. So we get the formation of ketone.
Yes.
Then Friedel-Crafts acylation reaction. So we can take benzene also. Here they have taken methoxybenzene. We can take only benzene also we can take. So on reacting with an acid chloride or acyl chloride in presence of anhydrous aluminum chloride. So we get mixture of para-substituted and ortho-substituted product. Para-substituted product will be the major product and it's a ketone. So this RCO is transferred to the benzene ring. RC double bond O benzene ring. It's a ketone. So nucleophilic addition of hydrogen cyanide. So cyanide will attack this carbon, pi electrons will go on oxygen. So we get this intermediate. So initially this is sp2 carbon, here it is sp3 carbon. So here it is trigonal planar geometry, whereas here it is tetrahedral geometry.
Yeah.
So this O minus, it will take H plus from the reaction mixture because it is HCN is there. It gets H plus from reaction mixture. So it will form this compound. This is called as cyanohydrin. So this reaction is, it can happen to aldehydes as well as ketones. So R1, R2, they can be alkyl, aryl, or hydrogen also. Both aldehydes and ketones undergo this reaction. So this was nucleophilic addition of HCN. Next, similarly, nucleophilic addition of sodium hydrogen sulfide or sodium bisulfite. So here the nucleophile is hydrogen sulfide or bisulfite. So as we can see, HSO3 minus is a very big nucleophile. So preferably aldehydes will undergo this reaction. Reactivity of ketones will be very low. So ketones are less reactive due to steric hindrance. So in ketones, two alkyl groups are bonded to carbonyl carbon. So steric hindrance is more. Here the size of nucleophile is also very, very big. So ketones are less reactive. So this sodium hydrogen sulfide, so suppose I do this reaction with the aldehyde. So with ketone also it can happen, but rate of reaction will be very low. The reactivity is less. Okay, suppose I do this with aldehyde. So the addition happens across the carbon-oxygen double bond. So HSO3 forms bond with carbon through oxygen atom. So it will forms carbon OSO2H. Then O minus will form bond with Na plus. And this occurs as crystals. We get a crystalline compound. So this is called as bisulfite addition compound or adduct. And it will be crystalline, so we can separate it by filtration. And then I can get back the aldehyde by treating this crystal with aqueous solution of an acid or aqueous solution of base, such as sodium hydroxide. I'll get back my aldehyde. Even ketone can undergo this reaction, but the reactivity will be low due to steric hindrance. So this is suitable for separation and purification of aldehydes. So I can create the crystals and then I can separate the crystals. The pure crystals I can treat with aqueous solution of acid or base. I'll get the pure aldehyde. Then addition of Grignard reagent. So aldehyde or ketone, the carbonyl carbon is electrophilic in nature. In Grignard reagent, the R can be alkyl or aryl. It is nucleophilic in nature. So this will attack this carbon. Pi electrons will go on oxygen. So R will form bond with carbon. Pi electrons will go on oxygen. O minus will form bond with Mgx plus. So we get this. So overall, this is a addition of Grignard reagent across carbon-oxygen double bond. So we get this. This is also referred to as adduct. And this on treating with aqueous solution of an acid. So hydrolysis happens over here. We get the respective alcohol. So in case of formaldehyde or methanol, so if I react a Grignard reagent with formaldehyde or methanol, I get primary alcohol. With other aldehydes, Grignard reagent with other aldehydes, secondary alcohol. Then Grignard reagent with ketones will give tertiary alcohol.
Yeah.
Then this reaction is not there. Okay, so next we are having nucleophilic addition of ammonia and its derivatives. So ammonia and its derivatives are commonly represented here as NH2Z. If Z is equal to hydrogen, it is ammonia. If Z is equal to some other group, it will be derivative of ammonia. So this is aldehyde or ketone. This represents aldehyde or ketone. So, so in ammonia or derivative of ammonia, nitrogen with its lone pair of electron will behave as nucleophile. In aldehyde or ketone, the carbonyl carbon is the electrophile. So nitrogen using its lone pair of electron will attack the carbon. Pi electrons will go on oxygen. this, so we'll have CO minus, R1, R2, and then here NH2Z. So nitrogen, after attacking this carbon, will get a positive charge. So the nitrogen will readily lose one hydrogen. It will lose a hydrogen. This O minus, it will take a hydrogen from the reaction mixture. So we get this product. So we get this one. Very often this is unstable. It will undergo elimination of water molecule. So OH from the carbon, H from the nitrogen, they will go out as water molecule, and we get this as the final product. Okay, so if Z is equal to H, then NH2Z will be ammonia. Okay, and the final product is called as imine. When Z is equal to H, final product is called as imine. If Z is equal to alkyl or aryl or amine, sorry, if Z is equal to alkyl or aryl, NH2Z will be called as amine. So it will be alkyl amine or aryl amine. And the product is, in this case also, it is called as imine when Z is equal to alkyl or aryl. Then if Z is equal to OH, then it will be NH2OH. This is called as hydroxyl amine. And the product, when Z is equal to OH, the product is called as hydrazone. When Z is equal to NH2, so it will become NH2Z will become NH2NH2. It is called as hydrazine. So when Z is equal to NH2Z is called as hydrazine. When Z is equal to NH2, so the product will be called as hydrazone. Okay. And if Z is equal to NHPH, so NH2Z will become NH2NHPH, where pH is benzene ring. This is called as phenyl hydrazine. And so if Z is NHPH, the product is called as phenyl hydrazone. Okay. Now in this phenyl hydrazine, on the benzene ring, if we are having the two nitro groups at position 2 and position 4, then it will be called as 2,4-dinitrophenyl hydrazine. It will be called as 2,4-dinitrophenyl hydrazine, and the product will be called as 2,4-dinitrophenyl hydrazone. Then if Z is equal to NHCONH2, then NH2Z. So NH2Z will be equal to NH2NHCONH2. So this is called as semi-carbazite, and the product is called as semi-carbazone. Okay, Achyut?
Yes.
When Z is equal to NHCONH2, it is called as semi-carbazone. Product is called semi-carbazone. Okay, so then reduction of aldehydes and ketones. So aldehyde upon reduction will give primary alcohol. Ketone upon reduction will give secondary alcohol. So reducing agents, we can use sodium borohydrate. So RCHO on using sodium borohydrate, we'll get RCH2OH. Or I can also use lithium aluminum hydride. Or I can use hydrogen gas in presence of finely divided palladium or platinum or nickel as catalyst. So I'll get RCH2OH. Similarly, from secondary alcohol on treating with hydrogen in presence of finely divided platinum or finely divided palladium or finely divided nickel, I'll get secondary alcohol from ketone. Sorry, from ketone, I'll get secondary alcohol. Okay, Achyut?
Yes, sir.
Then aldehyde and ketone can also be reduced to corresponding hydrocarbons. So this is Clemmensen reduction. So here this can be aldehyde or ketone. Aldehyde or ketone is reacted with zinc amalgam in presence of concentrated HCl. So we get the respective hydrocarbon and H2O is formed. Then Wolff-Kishner reduction. So aldehyde or ketone is reacted with hydrazine. So we get the formation of hydrazone. There is elimination of water molecule. We get the formation of hydrazone. And this hydrazone is reacted with potassium hydroxide in ethylene glycol as solvent. The reaction mixture is heated to high temperature. So we get the formation of hydrocarbon, respective hydrocarbon, and nitrogen gas is released. Okay, this is not anything significant. So aldehyde is oxidized to carboxylic acid. Aldehydes are quite reactive. They readily undergo oxidation to carboxylic acids using strong oxidizing agents as well as mild oxidizing agent like Tollens reagent and Fehling's reagent. Ketones, they resist oxidation. If we use strong oxidizing conditions, there will be cleavage of carbon-carbon bonds, giving rise to mixture of carboxylic acids. So then we have Tollens reagent, Fehling's reagent. So Tollens test. Tollens reagent is answered by aldehydes, both aliphatic, aromatic aldehyde. It is not answered by ketones. So Tollens test can be used to distinguish between aldehydes and ketones. So Tollens reagent is freshly prepared ammoniacal silver nitrate solution. Okay, so it in Tollens reagent, we'll be having silver nitrate, we'll be having ammonia, and there'll also be sodium hydroxide. So by mixing these three, we get the Tollens reagent, ammoniacal silver nitrate solution. So in this, so when I mix that, it will not be in the same way, it will get converted. So there'll be formation of silver ammonia complex will form. So this will be the active species. So aldehyde, suppose I have taken an aldehyde, it will react with this silver complex, and the medium is alkaline. Okay, so aldehyde will get oxidized to carboxylate, and silver plus, in this silver plus will get reduced to silver metal, and that silver metal occurs as bright silver mirror. Okay. So if I do this reaction in a test tube, I'll get the formation of a bright silver mirror on the walls of the test tube.
Yes.
Next, we have Fehling's solution, Fehling's test. Fehling's test is answered by aliphatic aldehydes. Aromatic aldehydes do not answer this. Ketones do not answer this. So Fehling's test can be used to distinguish between aliphatic aldehyde and aromatic aldehyde. And ketones also do not answer this test. So Fehling's test is done using Fehling's reagent, which is 1:1 solution of 1:1 mixture of Fehling solution A and Fehling solution B. Fehling solution A is copper sulfate solution. Fehling solution B is alkaline solution of potassium sodium tartarate. Potassium sodium tartarate tetrahydrate is called as Rochelle salt. So if I react an aliphatic aldehyde with Fehling's solution, Fehling's reagent, so the active species is copper 2 plus. So copper 2 plus, the medium is alkaline. So copper 2 plus will oxidize aldehyde to carboxylate, and copper 2 plus will get reduced to copper 1 oxide or cuprous oxide. This cuprous oxide is insoluble in water. It occurs as a reddish brown precipitate. Since copper 2 plus gets consumed over here, the blue color of the solution is discharged. Blue color of the solution goes away. It fades or disappears. And there is formation of a reddish brown precipitate of cuprous oxide. Okay, Achyut.
Yeah.
Then we have haloform reaction. So haloform reaction is shown by aldehydes and ketones, which contain at least one CH3 attached to carbonyl carbon. So, in case of aldehyde, it is only the acetaldehyde which can undergo this haloform reaction. In case of ketone, it will be called as a methyl ketone. So the respective compound, aldehyde or ketone containing methyl group, is treated with sodium hypohalite. So here carbon-carbon bond cleavage will happen. We'll get R1COO minus Na plus sodium. So this will get oxidized to carboxylate, and the methyl part that will get oxidized to haloform, such as, so if I use sodium hypoiodide, I'll get iodoform. This iodoform occurs as a yellow precipitate. So formation of yellow precipitate indicates that it is a methyl ketone. And this reagent, so NaOX, whether X is iodine or chlorine or bromine, it will not affect other functional groups. It will not affect the carbon-carbon double bond. That's what we see in this example. So nothing happens to carbon-carbon double bond. So the bond between carbonyl carbon and the methyl carbon breaks. So we get the carboxylate salt and chloroform. If we are using NaOCl, we'll get chloroform. Okay, Achyut?
Yes.
Okay. Okay, Achyut, that's it for today. Thank you very much.
Thank you, sir.
Thank you. Bye.
Thank you, sir. Bye.